welcome to the deep dive. Forget dipping a toe in, we're diving straight down, right to the absolute bedrock of building apps with Flutter. We've pulled together insights from a core guide, really designed to strip everything back and focus on the fundamental essentials. Flutter and its language, Dart.
That's right. I mean, you can certainly start using Flutter pretty quickly, right? Maybe copying examples. But to truly build something robust, performant, and importantly, to debug effectively, you really need to understand why the foundational pieces work the way they do.
Okay.
So we're starting right at the beginning, the language itself, Dart.
Okay, let's unpack this then. Because for anyone coming to Flutter, probably the first big question is, why Dart? It wasn't, the language everyone maybe expected for Google's big UI framework.
Yeah.
There must be some really specific, compelling technical reasons, more than just, oh, it's a Google language.
Oh, absolutely, yeah. And it really boils down to some unique characteristics that make Dart particularly well-suited for building UIs, especially UIs that need, both high performance and rapid iteration during development.
Okay.
One of the biggest advantages is its compilation flexibility.
Compilation flexibility.
Yeah. See, Dart supports two main ways of compiling. For release builds, when you ship your app, it compiles ahead of time, or AOT, directly into highly optimized, efficient native ARM code.
Native code.
And this is key. It means your Flutter app runs directly on the CPU, so you get that smooth native performance. We're talking 60 frames per second, or even higher for animations. And crucially, without needing some kind of performance-costing bridge to talk to the underlying platform.
Okay, so native speed for the final user hits the hardware directly.
You got it.
Got it.
Yeah.
But what about the developer side? Because everyone talks about Flutter's amazing hot reload.
Right. And that's the other side of the coin. That's powered by Dart's just-in-time, or JIT, compilation, plus a virtual machine, but only for development builds.
Oh, okay.
So while you're coding, you get this JIT compilation, and that, combined with the VM, enables this phenomenal hot reload.
Right.
You make a change, like to your UI code, hit save, and boom, within a second, sometimes faster, you see the updated UI on your device, your emulator.
And it keeps the state.
Often, yeah.
Yeah.
Without losing your application's current state, that loop. For iterating and testing UI changes, it's incredibly fast, a massive boost to developer productivity.
So the core takeaway on Dart is really that it uniquely offers both things: speed for the final app and speed for you, the developer, during the build process, purely because of how it handles compilation.
Exactly.
That balance seems pretty strategic.
It really is. It feels designed from the ground up with that balance in mind. And, beyond just compilation, Dart has other features really tailored for UI development.
Like what?
Well, it's object-oriented, strongly typed. Lots of people find that natural for structuring UI code. And its sound null safety system. That's a huge advantage you really notice as your code base grows.
Oh, yeah.
It catches those dreaded null reference errors at compile time, not crashing your app at runtime. So more reliability baked right in.
Okay, that's big.
Definitely. Also, Dart runs on a single-threaded event loop on the main core. It's kind of similar to how JavaScript works in browsers.
Right, single-threaded. Doesn't that block the UI sometimes?
Well, you might think so initially, but it actually simplifies UI development quite a bit. Avoids common multi-threading headaches like race conditions in your UI state.
Okay.
Asynchronous operations, which we'll definitely get to later, they're handled off the main loop. And if you do need heavy computation that really would block things, then you use isolate. Yeah, they're like separate memory isolated event loops, so you get parallelism, but without the typical shared memory issues. It's a cleaner model for concurrency when you need it. And that kind of brings us to its asynchronous model. It's fantastic, uses future, and this really clean async-await syntax.
Async-await. Familiar territory for some.
Exactly. And it lets your app do things like fetching data, accessing storage, slow stuff, without freezing the UI.
Crucial.
Absolutely crucial for a smooth user experience. The app stays responsive while it's waiting for that I/O to complete.
Right.
And one last thing on Dart. It's garbage collection. It's also optimized for UI workloads.
How so?
Well, Flutter's framework, it involves creating and discarding lots and lots of temporary short-lived objects as the UI updates. Dart's generational garbage collector is really efficient at cleaning these up without causing jank.
Those little stutters.
Exactly, those noticeable pauses that just break the feeling of smoothness. Dart's GC helps avoid that.
Wow, okay. That's a packed list of very specific technical advantages. It really wasn't an arbitrary choice at all.
No, not at all.
Dart genuinely brings a set of features specifically beneficial for building these high-performance reactive UIs efficiently.
Precisely. It provides that solid foundation for everything else Flutter builds on top.
Okay, so we have the language sorted, solid foundation. Now let's talk about the visible foundation of a Flutter app, widgets. Always hear the mantra, everything is a widget. What does that actually mean in practice? And what's the absolute core, fundamental difference between StatelessWidget and StatefulWidget? Because that's where everyone starts.
Yeah, everything is a widget really is the central concept. And it means, well, everything you see on the screen and even lots of things you don't see directly. Things that control layout or behavior.
Like padding or center.
Exactly. A button, text, padding, a column for layout, the whole screen itself. They are all instances of the widget class or, one of its many subclasses. And this brings us right to that fundamental split. StatelessWidget versus StatefulWidget.
Right.
A StatelessWidget, well, the name kind of gives it away. It describes a part of the UI that doesn't change dynamically once it's built.
Okay.
Its appearance is purely determined by the configuration, the properties passed into it when it's created. And that's it.
Like a title banner, maybe? Or an icon?
Perfect example is a static icon, a piece of text that won't change, an image that just loads once. It's simpler, less overhead, great for static content.
Makes sense. So, StatefulWidget.
Now, a StatefulWidget is what you use when the part of the UI you're describing needs to change, maybe based on user interaction or data coming in or some timer.
So anything dynamic.
Right. But here's where it gets interesting and honestly where it often trips people up initially.
Okay.
The StatefulWidget class itself, it's still immutable.
Wait, really? How does it change that?
Exactly. You can't change its fields after you create it. The dynamic changing part, it lives in a separate object.
Ah, okay. So the StatefulWidget isn't the thing that changes, it just creates the thing that changes.
You got it. The StatefulWidget's main job is actually pretty minimal. Its primary role is to create this separate, mutable object called the state object.
State object.
It does this using its createState method. And the state object, that's where you keep the data, the variables, that can actually change over time.
Right.
And the state object also holds the build method, the method that describes the UI based on that changing data.
Okay, so the logic and the changing data are in the state object.
Exactly. And when something happens that should cause the UI to update, like you tap a button, a counter needs to increment, you update the variable in the state object.
Like count plus n.
Right. And then, crucially, you call the setState method also within the state object.
SetState. Everyone sees that one.
And calling setState, usually you pass it a little function like setState plus var. That tells Flutter, hey, the state I care about here has changed. Please schedule a rebuild of this part of the UI.
It schedules it. Doesn't happen instantly.
It schedules it for the next frame, typically. Flutter is very efficient about batching updates. It then rebuilds that part of the widget tree, calling the state object's build method again. And now, build uses the updated data, the new count value, to return the description of the new UI.
So that's the cycle. Update data in state, call setState, Flutter calls build again with the new data.
That's the core loop for dynamic UI in a StatefulWidget. And just briefly, Flutter's pretty smart under the hood. It uses these things called element objects.
Element objects?
Yeah, they're kind of the glue. They manage the relationship between the immutable widgets and the mutable state objects. Critically, they preserve the state object across rebuilds, even if Flutter creates a new instance of your StatefulWidget configuration.
So that's how the counter value doesn't just reset every time build is called. The state object persists.
Exactly. The element holds on to the state.
That makes so much more sense now. So bottom line, if something needs to react and change its appearance dynamically, checkbox toggles, text changing, list updates, you need a StatefulWidget, and you use setState inside its state object to signal the change.
You got it.
Otherwise, if it's just static display based on initial config, StatelessWidget is the simpler, more efficient way to go. It's all about whether that piece of UI description needs to internally mutate over time.
Precisely. That separation is key.
Moving on then. There's this BuildContext parameter. It seems to pop up in almost every single Flutter method, especially, like you said, in build.
Everywhere.
What exactly is BuildContext and why is it so fundamental?
Okay, BuildContext. Think of it as an opaque handle. It points to the specific location of your widget within the overall widget tree.
My widget's address in the tree.
Yeah, that's a good way to think about it. When Flutter builds the tree structure, each widget gets its own context. This context is literally a reference to where that widget lives in the hierarchy. It gives the widget awareness of its position.
Okay, so it knows where it is.
Yeah.
Why does it need to know that?
Well, its main job, its primary use, is to allow a widget at a specific spot to find and access information or functionality that's provided by its ancestors' widgets higher up the tree.
Like looking upwards.
Exactly. For example, probably the most common one is theme.of-context.
Right, for colors and fonts.
Yeah. That dot of context method, it uses the context you give it to efficiently walk up the widget tree from your widget's location until it finds the nearest theme widget that's wrapping it. Then it returns the theme data from that ancestor.
Clever.
Same thing with navigator dot of context. It uses the context to find the nearest navigator state ancestor so you can, push a new screen or pop the current one.
Okay.
And state management solutions, like Provider, which we'll talk about, they rely heavily on context. When you use something like context.watch, you're telling Provider, use my current location, my context, to find the specific state object I need that was provided somewhere higher up in the tree.
So it really is like your street address. It lets you look up these services or data directories provided by your neighbors, but specifically the ones up the street or higher in the tree structure.
That's a really great analogy.
Yeah.
It's your connection point to the surrounding tree structure. And it's really important to remember that build contexts are local. They belong to a specific widget at a specific position. Meaning if you have, say, two identical raised button widgets, but they're in different parts of your UI tree, they will have two different build context objects. Each context knows its own unique place.
Okay, got it. Local addresses.
Yeah. And this locality is why you sometimes run into certain errors, like trying to use a context from a widget that isn't actually mounted, isn't in the tree yet, or maybe trying to use it after the widget's been removed, disposed of. Another common pitfall is trying to access something far up the tree, like showing a snack bar, using scaffold messenger dot of context. If you call that from a context deep inside a complex widget that is itself built by the scaffold builder, that context might be under the scaffold messenger in the tree structure.
So it can't find it by looking up.
Exactly. In those cases, you sometimes need to grab a context from a higher level, maybe using a builder widget, just to ensure the context you're using is definitely above the service you're trying to reach in the hierarchy.
It really ties each widget to its specific place and gives it that power to interact with the environment established above it. Fundamental indeed.
It absolutely is. It's the backbone for how widgets discover and interact within the tree. You can't really do much without context.
Okay, let's shift gears to layout. This is another area where Flutter often feels, distinct. Compared to, say, web development with CSS, how does Flutter figure out where everything actually goes on the screen? What are the core rules?
Right, layout. Flutter uses a very specific, very deterministic, constraint-based layout model. And honestly, mastering Flutter layout really boils down to understanding one core principle. It's often called the golden rule of Flutter layout.
The golden rule. Okay, I'm ready.
It is. Constraints go down, sizes go up, parent sets position.
Constraints go down, sizes go up, parent sets position. Okay, sounds like a strict contract. Let's break that down piece by piece.
Absolutely. It is a contract between a parent widget and its child widget. So first, constraints go down.
Okay.
When a parent widget needs to lay out one of its children, it passes down a constraint object to that child. Now, this isn't a suggestion. It's not a preferred size. It's a set of boundaries. Minimum width, maximum width. Minimum height, maximum height.
A box that has to fit in.
Exactly. And the crucial part is the child must choose a size for itself that fits entirely within those constraints. It cannot be smaller than the minimums the parent set, and it cannot be larger than the maximums the parent allowed. It's bound by them.
Strict. Okay, step one. Parent gives boundaries. What's next?
Second, sizes go up. So the child widget receives these constraints from its parent based on those bounds and also its own internal logic, like does it want to be as big as possible? Does it want to wrap its content?
Yeah.
The child then determines its own actual size.
Within the rules, though.
Absolutely. The size it chooses must be valid according to the constraints it just received. Once it has picked its final size, it reports this size back up to the parent widget.
Okay, so child says, okay, within your rules, I've decided I'm this big.
Precisely. And finally, third step, parent sets position. Now that the parent knows the specific chosen size of each of its children, because they reported their sizes back up, the parent widget is then responsible for actually positioning those children on the screen.
Okay.
So like a column widget, it gets constraints from its parent. It then passes constraints down to its children, maybe giving them its full width but flexible height. It gets their chosen heights back up, and then it positions them vertically, one below the other based on those heights.
Right. Or a center widget might give its child really loose constraints, like be anything up to the screen size.
Exactly, allowing the child to maybe choose its own natural size.
And then the center just positions that chosen size right in the middle.
You got it. Or a container with a fixed width and height. It passes down tight constraints, where min width equals max width equals the fixed width. It forces the child into that exact size.
So the parent always dictates the boundaries first. The child chooses its size within those boundaries. And then the parent decides where that size child actually goes on the screen. It's not like the child just says, I want to be this big, and the parent has to figure it out.
Exactly. That's the key difference from some other layout models, like maybe HTML, CSS sometimes feels. In Flutter, the parent always imposes the limits first. The constraints flow down before any sizing decisions are finalized going up.
Okay.
This rule, this strict flow, is absolutely fundamental to how Flutter achieves efficiency and predictability in its layout calculations. It avoids multiple layout passes in most cases.
And this explains those overflow errors, the yellow and black stripes.
Perfectly. A render flex overflow, or similar layout error, literally means a child widget tried to be bigger than the constraints its parent gave it. It violated the contract. So understanding this rule, constraints down, sizes up, parent positions, is absolutely essential for debugging layout problems, widgets like expanded or flexible. They're basically tools that allow parents like row or column to give flexible constraints to their children within that system.
It sounds maybe a bit rigid at first, but I can see how once you internalize that parent-child contract, layout issues probably become much clearer to diagnose. Okay, who gave who the wrong constraints, or why did the child ignore the constraint?
Exactly. It gives you a clear model to reason about.
Yeah.
And it provides the predictability needed for Flutter's rendering pipeline to be so fast.
Okay, brilliant. Now, we touched on set state earlier as the way to make a stateful widget dynamic. Is that the whole story when it comes to managing state, especially in like a more complex application?
State management. Yeah, set state's absolutely the fundamental tool. It's for managing local mutable state that's confined purely to a single StatefulWidget's associated state object.
Right.
It's perfect for simple things. Toggling a Boolean to show hide something, managing the current value of a slider, that counter example we keep using.
Yeah.
You update a variable inside the state object you call setState. Flutter schedules a rebuild, UI updates. Simple, effective for local scope. But as your application grows, relying only on setState, well, it quickly runs into limitations. It doesn't scale well for certain scenarios.
Okay, like what kind of limitations?
Well, the first big one is probably code complexity and just clutter.
How so?
Imagine you have some piece of state, let's say, whether a user is logged in or not, and maybe lots of different widgets scattered across different screens need to know that information.
Right, like the app bar, the profile page, maybe some content sections.
Exactly. If you only have set state, the only way to share that is logged in state is to put it in a stateful widget that is a common ancestor to all those widgets that need it. Usually that means putting it way up high in the widget tree, maybe near the top of your app.
Okay, lifting state up.
Right, lifting state up. But then you have to pass that is logged in value and maybe a function to change it down through potentially many, many layers of widget constructors just to reach the actual children far down the tree that need it.
Oh, I see. Passing it through widgets that don't even care about it themselves.
Exactly. That's what's known as prop drilling. Your widget constructors become bloated with parameters that are just being passed through. Your code gets harder to follow, harder to refactor, harder to maintain. It couples widgets unnecessarily.
Yeah, that sounds messy.
It can get very messy. Second big limitation, set state isn't really suitable for global application state or state that needs to persist beyond the lifespan of a single screen or widget.
Like user settings or a shopping cart.
Perfect examples. Stuff that needs to survive navigation or maybe even app restarts in some cases. Set state is tied to the lifecycle of a specific state object, which is tied to a specific location in the tree.
Got it.
And while Flutter's rebuild mechanism is generally very efficient, if you're not careful, misuse of set state can potentially lead to performance issues. You might accidentally trigger rebuilds of very large, complex parts of your widget tree when only a small part actually needed to change.
Right, calling setState too high up the tree unnecessarily.
Yeah, and one more thing, you have to be a bit careful when dealing with async operations. If you say fetch data with a wait, and then you want to call setState with the result, you need to make sure the widget is actually still mounted, still in the tree before you call setState, because the user might have navigated away while you were waiting for the data. If you call setState on an unmounted widget, you get an error.
Okay, so you need that if mounted check sometime.
Exactly that check. So yeah, setState is your fundamental tool for local widget state, but it has clear limits.
So, summary. While setState is the go-to for a single widget managing its own little world, if you need state that's shared across multiple widgets or across screens or needs to live longer, you really need something more sophisticated to avoid ending up in a tangled mess.
Exactly right. You need a dedicated state management approach.
Which naturally brings us to Provider. Probably the most commonly recommended starting point for state management beyond setState. How does Provider tackle these challenges?
Right, Provider. It's a really fantastic helper package. It essentially builds on top of Flutter's own built-in mechanism for passing data down the tree called inherited widget.
Inherited widget. I've seen that, but it looks a bit complicated.
It can be a little verbose to use directly. Provider basically wraps inherited widget, making it much more convenient and easier to use for common state management patterns.
Okay, so what does it let you do?
It lets you provide some state, or really any kind of object, like a service class, a repository, to descendant widgets down the tree without having to manually pass it through all the intermediate constructors. It solves that prop drilling problem directly.
Oh. Magic.
Not quite magic. It uses the build context we talked about earlier.
Context again.
Always context.
Yeah.
So instead of passing data down manually, you wrap a section of your widget tree, maybe your whole app, or just one screen with a provider widget. This provider holds an instance of the object you want to share, like your user profile model or shopping cart.
Okay.
Now, any widget below that provider in the tree hierarchy can simply ask for that object using its build context.
How does it ask?
There are a few ways, but the most common are using methods like provider.ofyourObjectType context or the shorthand context.watchYourObjectType, or using special consumer widget. Context.watch is particularly useful because it does two things. It gets you the object, and it tells Flutter that this widget should rebuild whenever that object signals a change.
Oh, so it sets up a subscription automatically.
Exactly. It handles the listening part for you. So a really common pattern with Provider is to use it with something called a change notifier.
Change notifier?
Yeah, it's a simple class provided by Flutter itself.
Right.
You create your own class for your state, say cart model, and you make it extend change notifier. Inside cart model, you have your list of items, methods to add or remove items, etc.
Okay.
Then, somewhere high up, you wrap your app or screen with change notifier provider, telling it to create and provide an instance of your cart model.
Right.
Now, down in your UI, maybe in your cart screen widget, you use context.watchCartModel to get the cart model instance. And maybe in your app bar, you use context.selectCartModel in part.itemCount to just watch the item count.
Select for just watching part of it.
Yeah, for optimization. Now, when something happens, say, the user taps an Add to Cart button, you call the addItem method on the cart model instance. Inside that method, after adding the item, you call notify listeners. Right. That's the magic signal from change notifier. Provider hears that notify listeners call, and it automatically triggers a rebuild for only the widgets that were watching that cart model using context.watch or consumer.
Wow. Okay, that is clever. So the state logic, like adding items to the cart, lives completely separate in the cart model.
Exactly.
And the UI widgets just declare, hey, I need the cart model, or I need the item count from the cart model using context. Provider handles delivering it and telling them when to update.
Precisely. It decouples the state logic from the UI widgets. Your widgets become simpler, they just consume state. Your state logic is centralized and easier to test. It elegantly solves prop drilling by making the data available via the tree structure itself, powered by context.
That sounds so much cleaner.
It really is. And Provider is often recommended by the Flutter team itself, especially for simple to moderate app state needs, because it leverages Flutter's core concepts like inherited widget and build context so well. It feels very Fluttery.
It definitely sounds like a much cleaner, more scalable way to share data and state across your app compared to just trying to wrestle everything with set state and prop drilling.
Absolutely. It's usually the next logical step once set state starts feeling painful for shared state, a critical tool in the toolbox.
Okay, final core topic for today. handling things that, well, take time, like pulling data from an API over the internet or reading a big file from disk. How does Flutter manage those asynchronous tasks without just freezing the user interface while it waits?
Right, async operations, super important. As we mentioned earlier, Dart runs on that single event loop on the main UI thread. That's where all the UI building, drawing, user input handling happens.
The critical thread you can't block.
Exactly. Blocking that thread means a frozen, unresponsive app, the worst user experience. So to avoid blocking during slow operations like network requests, which mostly involve just waiting, Dart uses asynchronous programming. The main tools for this are futures and streams.
Futures and streams, okay.
Let's start with a future. A future represents a single result that will become available at some point in the future.
Like a promise.
Exactly like a promise in JavaScript or a task in C#. It's a placeholder for a value that isn't ready yet. That value could be the data you requested from the API, or it could be an error if something went wrong during the request.
Okay, a promise for one result later.
Yep. Think of it like placing an order online. You get an order confirmation, the future, and you'll get your package, the result, later.
Got it. How do you work with them?
The most common and cleanest way these days is using the async await syntax.
Oh.
You mark a function with the async keyword. Inside that function, you can then use the await keyword before calling any function that returns a future, like await http.get to make a network request.
Right.
Now here's the crucial part. When Dart hits an await, it pauses the execution of that specific async function right there. But, and this is key, it does not block the main event loop.
So the rest of the app keeps running.
Exactly. The main thread is immediately freed up to go off and do other things, handle user taps, run animations, rebuild other widgets. It stays completely responsive. Then, when the future you were awaiting finally completes, either with data or an error, the event loop schedules your paused async function to resume execution right after the await statement where it waited off.
That's really elegant. It looks synchronous, but it's non-blocking.
It makes asynchronous code so much easier to read and write compared to chains of callbacks, the old way.
Definitely. So that's futures for single results. What about streams?
Right, a stream. While a future is for one result, a stream represents a sequence of asynchronous events or values that can arrive over time.
Like a flow of data.
Exactly, like a flow or a pipe. Think about things like real-time updates from a database like Firestore. You might get an initial snapshot, then updates whenever data changes, or user input events like mouse movements, or reading a large file chunk by chunk. These are ongoing sequences, not just one single result.
Okay, and how do you handle those?
You typically interact with streams by listening to them. You call the .listen method on the stream and provide callback functions. One for when a new data value arrives on data, one for errors on error, and one for when the stream closes on done.
So you react to events as they come in.
Precisely. Alternatively, within an async function, you can use an await for loop, which is syntactically nice. It loops through the stream's events as they arrive, kind of like a regular for loop, but asynchronous.
Await for, interesting.
And the real beauty of this whole async system in Dart Flutter is that because these async operations eventually complete back on the main event loop when the future resolves or stream event arrives, you are already on the correct thread to safely update your UI state.
So no complex thread marshalling needed.
Generally, no. When your await finishes or your streams on data callback fires, you can directly call setState if you're using StatefulWidgets locally, or update your state model if using Provider or similar, and Flutter will handle the UI update correctly. It fits very naturally with the UI framework.
That's a huge simplification compared to some other platforms.
It really is. Oh, and of course, you typically wrap your await calls in try-catch blocks to handle potential errors from the future gracefully.
Right. Error handling is important. So,
yeah.
Okay. Futures for one-off async results, streams for ongoing series of results, and async await makes working with futures much cleaner, all while ensuring that critical main thread stays free, keeping the app smooth and responsive even when doing background work.
You've nailed it. That's the core of handling asynchronicity in Flutter. It's fundamental for any real-world app that needs to interact with the outside world.
Wow. We have covered a significant amount of ground today, really diving deep into these core concepts that make Flutter what it is. We looked at why Dart was chosen, those specific compilation and language features. We dug into widgets, immutable blueprints, StatelessWidget versus StatefulWidget, and that separate mutable state object.
Yep.
But we demystified BuildContext as the widget's address in the tree, enabling communication upwards. We tackled the layout system's golden rule, constraints down, sizes up, parent position.
Here's your rule.
We explored state management, starting with the basics of set state for local state, and then understanding its limitations and how solutions like Provider offer a cleaner way to handle shared or complex state.
Moving beyond set state is key for scale.
And finally, we just covered how Flutter handles asynchronous operations using futures, streams, and async await to keep the UI responsive.
Yeah, a lot of foundational stuff. And I think understanding the why behind them, why constraints work that way, or how the event loop plus async allows for both performance and relatively simple code, that's really key. It helps you move beyond just copying code snippets to actually reasoning about your application's structure and performance.
It definitely feels like it requires shifting your thinking a little bit, especially if you're coming from, say, web development or maybe native Android OS directly. But seeing how these pieces, Dart's features, immutable widgets, the state separation context, the layout contract, async handling, fit together as a cohesive system, hopefully this deep dive has clarified some of that unique Flutter philosophy.
Absolutely. And maybe one final thought is to consider how these foundations aren't just isolated features. They really work together. Think about how mastering that constraint system fundamentally changes how you approach building responsive UIs compared to CSS media queries, perhaps.
Right.
Or how internalizing the immutable widget plus mutable state pattern changes how you think about triggering UI updates, moving away from direct manipulation towards declarative descriptions based on state. These aren't just technical details, they're powerful paradigms built right into the core of the framework. Understanding them unlocks a lot.
That's a great point. It's about the mindset shift as much as the technical details. Well, thanks for joining us for this deep dive into Flutter's fundamentals. We really hope this helps you build a stronger foundation for your own Flutter development.